So our next speaker is Gabriel, and he will be presenting the paper on algorithmic interval decomposition for persistence modules of free Abelian groups. This is a joint work with Gregory, Henselman, Petrusek.
Yeah, okay, so I was going to say all that myself, but you, I guess, leave me to it for the introduction. So I guess like just an overview of what this work is roughly speaking about. So we talk about persistence modules of free Abelian groups and their interval decompositions. So persistence modules, as I guess was just discussed a moment ago, they're algebraic objects that are of great importance to persistence homology. And when we deal with field coefficients, we get these things called interval decompositions, which basically give us the necessary information for computing persistence diagrams, essentially. The thing about these interval decompositions is that they do not actually exist when we are outside the setting of field coefficients. So in this particular work, we deal with persistence modules of free Abelian groups, which are Z modules, and we prove necessary and sufficient conditions for when interval decompositions of these things exist. And we also provide an algorithm for computing interval decompositions, provided one actually does exist. So I guess starting off, let's just quickly do some introduction. So in a persistence module is essentially a functor from finite totally ordered poset to the category that's given by a finite totally ordered poset to the category of R module, where here R is a PID. So essentially what we can do is we can think of this as a sequence of R modules with maps in between. And we can of course also compose these maps in some sort of manner. Persistence modules, so these arise naturally from persistence homology, where essentially, given the filtration K0 through Km, we can apply homology with coefficients in some ring to get a persistence module over that ring. And we're going to call so the maps in between the R modules, we're going to refer to them as structure maps, and in the context of persistence homology, these structure maps are given by the inclusion map. And something else is that throughout this talk, we're going to assume without loss of generality that the first and last things in our persistence modules are both zero. And of course, we can just do this because we can always tag on zeros to the beginnings and ends of persistence modules without losing anything. All right, so now let me talk about what an interval module is. So essentially an interval module is a persistence module that has two parameters B and D, where essentially what we have is that in between B and D, specifically when we take an index I and it's greater than or equal to B and less than D, then that persistence module valued at I is precisely R, and otherwise it's zero. And the maps in between, so the structure maps in between them are going to be given by either identity if it's between two copies of R, and it's zero otherwise. So an interval decomposition for a persistence module is essentially a direct sum decomposition of F into into a bunch of interval modules. And essentially what we can also think about this is essentially we can also think of this as choosing a basis for each of the Fi's, such that if we take a structure map F from A to B, then essentially basis elements at A get mapped to either zero or to basis elements at B in some sort of injective manner. If that makes sense. And a fact that we have is that when R is a field, then persistence modules always exist. We can always have a decomposition. Interval decompositions always exist. We can always decompose persistence modules into the direct sum of interval modules. So right in our work, we focus on when the persistence modules are valued over the integers. have coefficients in the integers, I should say. Essentially, what this means is, our ring is integers, and we also additionally assume that each of our, modules in our persistence modules is free. So essentially, the target category for our persistence modules is given by free Abelian groups. And essentially, the theorem that we prove is the following. We're basically given a persistence module of finitely generated free Abelian groups. We prove that, our persistence module splits as a direct sum of integral modules if and only if the co-kernel of every structure map from A to B is free. So this is, I guess, our big theorem. And I'm gonna, kind of explains the rough picture of how we end up proving this thing. So, can we, yeah, okay, this is one. So one of the directions of this is actually fairly simple, and essentially that direction is that if we have, if we have an interval decomposition of a persistence module, then we can show that the co-kernel of every structure map is free. So to do this, of course, what we can do is, given our persistence module of interest, we can, write it out as, write it out as a direct sum of interval modules, and then we can fix some A and some B. And then we can essentially choose the indices I that correspond to interval modules that are non-trivial at B. So basically are not zero at the index B. And then from this, we can split N into two pieces. The parts that are like the indices that are not trivial at A and the indices that are trivial at A, right? So from this, what we can do is if we want to write out, F to B, what we can do is, first write it out as a direct sum of, the interval modules value at B. But the thing about this, of course, is that we only need the things that are non-trivial at B, because otherwise it's just zero. So that's how we have the second line. And to get from the second to third line, we just use the fact that, N can be, split up into X and Y. Here, X and Y are the non-trivial and trivial parts of N the parts of N that are trivial and non-trivial at A. Now, to get the last, line, how we can do this is basically realize the fact that if we look at the first summand on the third line, what we get precisely is the interval modules that are non-trivial both at A and at B, right? And as a result, one can show that this is essentially, the image from F. Yeah, the image of the structure map from F of A to B. So knowing all this, what can we do? Well, what we're interested in this, context is we're interested in the co-kernel, and the co-kernel we can get by basically taking FB and modding out by the image of the structure map F from A to B. Now the thing about this, the thing about this quotient is that it's actually precisely isomorphic to the right-hand side. The right-hand guy, the direct sum with indices in Y. And that thing we know is free. So therefore, our co-kernel of interest is in fact free. So the other direction, as I might have hinted, is that so our other direction, which is that if we have every co-kernel being free, every co-kernel for every structure map being free, then we necessarily get a direct sum decomposition of our persistence module and interval modules. Sorry. So this is a little more difficult. This requires a little more steps. And essentially to do this, what we do is for each of our groups Fi, we study something called a secular lattice, which is basically, sorry, this should be singular, not plural, whatever. Yes, anyway, so we study the secular lattice, which is essentially a subgroup lattice generated by kernels and images that arise from the persistence module F. And then we prove the existence of complements for nested pairs of things in the secular lattice. And using these things, we essentially decompose the groups Fi into, corresponding or in the corresponding sort of manner, which I'll explain what all of this means, but this is essentially the step that we kind of take to, go about this. Right. right, so now let me talk about the secular lattice. So essentially the secular lattice is defined as follows. So given some a, from value, given some a from 1, 0 through m, we can define, the cur a comma y to be the kernel of the structure map from a to y, given that a is less than or equal to y and 0 otherwise. So essentially this can be, so the family of all these, cur a comma y, these are basically the kernels of the structure maps that originate at a, right? And similarly, we can define mx comma a to be something similar, where essentially it's like when x is less than or equal to a, it's the image of the structure map from x to a, and otherwise it's just fa. And this too can be kind of thought of as like, a family of images that's end in a. And essentially the secular lattice of fa is a lattice of subgroups of fa that's essentially generated by all of the m x comma a and cur a comma y's. So here we have the two lattice operations, me and join, which are given by the sum and intersection of subgroups. And in particular, yeah, so it's essentially, if we take meets and joins and all that stuff and make things close, then we get the secular lattice. Okay. So now I'm going to talk about a slightly different lattice, which is the lattice of down closed sets. So in this setting, what we have is we have the set Mn, which is essentially the cross product between 0 through m and 0 through n, where m and n are integers. So we say that a subset is down closed if whenever we have p comma q in S, then p prime and p prime comma q prime is also in S whenever p prime is less than or equal to p and q prime is less than or equal to q. So what this in particular means is that if we have such a thing here, then if we have this point, we have everything below it and everything to the left of it. So basically, this point's in it, everything here must be in it as well. And these are some examples of down closed sets. So here we have xm and mx, which in fact actually generates this lattice. And then we have some other guy here. Right, so as I said, essentially like how we should think of this, essentially, if we have a point here, then everything, to the left and below it are, necessarily also in this down closed set. So I guess the whole point of this is that if we consider all the down closed sets of, Mn, then this forms an order lattice where the join and meet operations are given by unions and intersection of these subsets, these down closed subsets. And yes. Yeah, so yeah, this forms a order lattice on the subsets of Mn. So part of the reason why, so actually pretty much the entire reason for why we discussed this, other lattice lattice of down closed sets is because in some ways that it essentially indexes things in the secular lattice in curve fa. Namely, we have the following theorem that allows us to relate things between the two of them. So essentially, we have a lattice homomorphism from the down closed sets to the to incur fa, the secular lattice of fa, where essentially we have the following, we have xm going to m of x comma a and my going to the curve of a comma y. So something to note is that this essentially maps generators from one, poset category, from one lattice to generators in another lattice. And we call this the secular homomorphism co-restricted to A, which we denote by big lambda of A. So with all this said, let me kind of just talk a little about, this secular lattice. So the first thing I should do is define what it means to have complements. So we say that C is a complement of A, and B if essentially C or B can be written as direct sum of A and C. So with that said, what we have is that if we have a nested pair of subgroups in the secular lattice, then necessarily the smaller one must have a complement in the bigger one. So that's one of the things that we proved. Something else that we're able to actually also prove, using this in fact, is that we can actually, for each of the FAs, we can choose essentially a family of subgroups Aija in FA, such that if we want to take, any S in our downclosed set, if we want to take any S and we look at the, lambda A of S, then lambda A of S is exactly a direct sum of the Aij of A of sub A's, that where the I and J are indexed by the things in our downclosed ZS. So in some ways, the Aij's essentially give us building blocks for things in the secular lattice, or it gives us like building blocks in the secular lattice that we're just in. Okay, so the last bit I think is actually worth mentioning, except for the fact that it's like cut off, so I'm not really sure how to fix that. But essentially, in the context of persistent homology, what we can do is we can kind of view the Aij's as essentially the cycles that are born at I and die at J. So this is one way we can kind of like view what the stuff actually is. So in fact, we can actually choose the Aij's in a more sort of powerful sort of way, where essentially if we restrict one of the, so if we take one of our structure maps from A to B, and we look at the image of Aija, we can choose the Aij's in such a way where essentially Aija gets, like the image of that is inside Aijb. Moreover, something else that we can show is that the Aij's, so this is 0 whenever A is out, it's not in between I and J, and in this case, in between means A is, A is less than I, or A is greater than or equal to J. So whenever we're like not between I and J, then we can show that this thing is actually equal to 0. Something else we can show is that when our indices A and B are in between I and J, then the structure map from A to B restricts to isomorphism between Aija and Aijb. And with this, what we can essentially do is we can decompose our persistence module F into a direct sum of these things which we refer to as generalized interval modules. Now, okay, so essentially given one of these generalized interval modules, Aij, essentially this is made up of all the Aij's, for every A. And in particular, we note some important things, notably these two things. And the thing about these two things is that if we recall how interval modules are defined, these should, in some sense, remind us of interval modules. And in fact, what we can show is that each of the Aij's, so each of the generalized interval modules can be written as a direct sum of interval modules themselves. And this essentially, I guess, completes our proof in the sense that our persistence module F can be written as the direct sum of generalized interval modules, which themselves can be written as the direct sum of interval modules. And therefore, we have a direct sum of interval modules for F. And therefore, we have an interval decomposition. All right, so I guess with the last few minutes, I'm going to explain this sort of algorithm, which is not cut off, so that's good. So let me. I'm going to basically alternate between these two slides. Oh, wait, not that one. So essentially, what we're doing in this algorithm is we're basically, we're building up our bases one at a time. So we're starting from the left, and then we're working our way to the right. What we're essentially doing is first we're inheriting whatever basis we got in the previous iteration, and then we're building up from that. So specifically, how are we doing that? Well, what we're doing is that okay. So essentially, what we get is by okay, how can I say this? So what we first do is we take the basis from the previous guy, we push it over from this with the structure map from I minus 1 through to I, and then we basically throw out the 0 stuff. Now, what we can show is that, this is in fact linearly independent, and essentially what we do is we start tacking on these things, and these things are essentially these are essentially bases for complements of this guy in this. So essentially what we're doing is we're building up. So let me actually go to this slide for a bit. So essentially what we're doing is we're iteratively completing our basis into a basis for m I minus 1 comma I plus the kernel from I to j. We're starting of course at j equals I, but essentially this ends when j equals m, and the reason why is because, as we noted earlier, m or like fm is equal to 0, which means m I comma m is equal to fi, and therefore this whole thing is equal to fi. So ultimately we do end up with a basis at I. Something to note is that essentially the basis that's produced by this algorithm contains essentially a basis for every kernel and every image given by the structure maps, and in essence, this gives us our a basis that yields or that corresponds to an interval decomposition. Okay, so I guess like really to summarize this work, and this is the last slide. Essentially, we proved the following theorem that a persistence module of finitely generated free Abelian groups can be written as can be interval or has an interval decomposition whenever all the structure maps are have free co-kernel, and we additionally produce an algorithm for computing an interval decomposition when one exists. And yeah, that's it.
Question, please. Yes. Thanks for the talk. So both the result and the proof seem to heavily rely on the fact that you're using conditions.
Yes.
Are there any ideas how to extend this or how to look into?
This is something actually. Yeah, so this is something I've been thinking about trying to extend towards. One of the things is that like the degrees of torsion, I have a feeling that the different degrees of torsion may have to be treated separately, which almost certainly will be a lot more complicated. Yeah. But yeah, no, this is definitely something I'm, I guess, thinking about, but don't really have any real, I guess, concrete ways to make the extension right now.
So there is a question that's popped up on the internet.
Yes. So the question is, are there minimal conditions so that all co-kernels are free? Or do you have to check all the pairs A comparable to B?
Yeah, so I guess like okay, so I guess I could answer this in two ways. So the first way is like, I guess one can first check them manually, or like check all the pairs manually, which of course is kind of annoying to do. There is kind of another way to get around this. There's kind of a way to get around this, which is a little more complicated. Basically, we produced this algorithm, but we also produced one that's like a little more, I guess, in the flavor of matrix algebra, which kind of like does the whole checking of co-kernels, or checking of the freeness of co-kernels. So so the answer is like, well, I don't know if it's minimal necessarily, but it's certainly a lot less, like annoying than checking, all such A's and B's with A less than equal to B. Yeah.
Let me ask you one question.
Oh, yeah.
Did you ever analyze the algorithm? How much is the time complexity?
It should be polynomial.
Polynomial.
Yeah. So that's the thing. I did not look into much.
Because that question is related, whether you have to check pairwise, that will be costly.
Right. Yeah. Right. So with that, I guess like the answer is no. That probably is something we should do. Yes.
You maybe haven't thought about this, but if you did have torsion. And you. Would your ideas give you the torsion free part of
Okay, so I guess one of the issues with torsion is that you can have torsion free parts mapping into torsion parts, which might give you a little bit of free. I'm not sure about that. There might be a way to do this, but surely
So your commodity is also over the,
wait, sorry?
so the commodity is also over the,
Yes.
so your barcode or interval cannot describe the portion part, now the portion free part.
Wait, sorry.
So
I don't think I caught that.
The commodity has the portion part and the portion free part. And under the decomposition and counter say the difference between the portion part and the portion free part.
Like, what can I say about the difference between torsion free and torsion parts of homology?
A generator can be a torsion generator, but between commodity and the interval bar, and just that the generator and first and die actually after because an offset it is whether the generator is torsion or torsion free.
So, okay, I'm gonna repeat what I think I heard, and you can tell me if this is the question you have answered. Like, is a question something along the lines of what is it if, like, how to interpret torsion parts and torsion free parts of homology groups?
This is the overlay, so more is more complex. So the decomposition, the decomposition is not convert to all the information or cover all the information of the homology. If the coefficient field, the coefficient of ring is the field, the barcode and the position homology are different representation, but they are equivalent. But for overlay and it seems not equivalent.
Right, because you have the well, I mean, I guess overseas you don't necessarily have a persistence diagram at all.
Well, we'll never have a that
Well, you may not, like, you're not guaranteed one. I mean, the whole thing here is that, like, you might. So the interval decompositions are, like, essentially equivalent to, like, essentially the points in the persistence diagram are given like the points in the interval decomposition. And if one doesn't exist, then. Sorry, I'm not really sure if I'm understanding your point.
Maybe I have to intervene now because of the time's sake.
Yeah, we can talk.
Yeah, you can take the